Good afternoon, everyone. I'm Shuai Wang, and I'm from Penn State University. So in this talk, I'm going to present our research on identifying some cache-based timing channel in the production software. So this work is joined with Wang and Xiao, who is also here today, and Dr. Danfeng Zhang, and my advisor, Dr. Dinghao. Okay, so let's get started. So this is the outline of my talk. I will start with some background information in the context. So generally speaking, this research tries to identify some vulnerabilities in the software system, which can be further utilized for the cache-based timing channel attack. To get you familiar with the context, I will use some examples along the presentation. So the general attack scenario is like this. Suppose I have a victim program which takes some secret as an input. And the attacker can either directly or indirectly observe the trace of cache status in terms of hit or miss. Suppose I give the program a secret, and the attacker observes a trace of hit or miss. And with another secret, the attacker would observe another trace of hit or miss, the cache status. So by comparing the observed traces and identifying some difference in the cache status, in this case, the attacker would be able to infer like which secret is given to the program, and as a result, some secret information will be recovered from the process. So actually, such kind of vulnerability has been found in many real-world cases. So here I will show you two typical vulnerable patterns regarding the cache-based set channel attack. So the first one is called secret leakage dependent control flow. The second one is called secret dependent memory access. So here's an example showing the first case. So essentially, the array E is an array of program secrets. And the if condition checks whether the corresponding array element equals to 1 or not for each loop iteration. So if the if condition holds, then the statement in the red box will be executed. And the problem is that, like Flex just mentioned, the attacker can use some prime and probe technique to check corresponding cache line and decide whether a statement in the red box is executed for each loop iteration. And as a result, the corresponding array element of the program secret can be recovered for each loop iteration. So actually, such kind of vulnerable patterns has been found in the square and multiply implementation of the modular exponentiation. And some real vulnerabilities have been found in the RSA and the ElGamal decryption routines. So the second case is called secret dependent memory access. So even though there's no explicit dependency of the program control flow on the secret, but still there are some critical issues here. So like shown in this example, for each loop iteration, a window size of the secret key will be extracted into a variable, the IDX. So later, the IDX will be used to query a table in the statement in the red box I highlighted. So the problem is that still the attacker can use some prime and probe technique to check corresponding cache line and decide and recover certain information in the variable IDX. So as a result, for each loop iteration, certain secret information will be recovered from the window size of the key. So such malicious patterns can be found in the sliding window-based modular exponentiation. And some real-world vulnerabilities has been found in the AES, RSA, and also the ElGamal decryption implementations. So generally speaking, there has been some research trying to identify the first vulnerable pattern. So in this project, our major focus is on the second one. So we try to deliver some technique to identify the secret dependent memory access and analyze how it will affect the cache behavior. All right, so this is the threat model of this project. So essentially, we assume the attacker would share the same hardware platform with the victim, which is like pretty standard assumptions. And we assume the attacker can either directly or indirectly learn the trace of cache line being accessed. So generally speaking, our threat model is stronger than those based on cache status, the hit or miss. But on the other hand, a trace of cache line being accessed can mostly determine the cache status at any program point. And another thing is the cache line-based model makes the vulnerability analysis more general because our abstraction, the model does not is independent of the cache line implementation details. All right, so existing work in this direction has proposed some technique to prove the absence of the set channel in the software system. So essentially, they try to deliver some overestimations to identify the upper bound of the information leakage. And also, they are mostly unable to provide some counterexamples that can actually trigger the suspicious vulnerable points. And also, they may suffer from some scalability issue. So considering the design choice of existing research, so in this work, we try to propose a technique which can identify some cache-based timing channels in some large-size software system. So essentially, we try to identify the variance in the cache line access trace. And we try to propose a technique that can actually deliver some counterexamples. For example, different program secrets that can actually trigger the suspicious vulnerable point. We try to make our technique scalable enough, which can be adopted to the real-world software system. So before I jump into the technical details, let me first brief the structure of the set associative cache. So we hope to use this example to get you understand how we connect the program memory access with the program cache line access. So essentially, the minimal storage unit of a cache is called a line, and the cache is divided into sets of equal number of lines. So for a memory address of n bits, essentially the middle part is called a set index, which is used to locate the set where the data may be stored. And the upper part is called a tag, which is used to confirm whether data is presented in one of its cache lines. And the lower part is called a line offset, which is to locate the data inside the cache line. So as you can see, essentially for a memory address of n bits, the upper n minus l bits would map a memory access to its corresponding cache line access. And it is actually relevant to the timing because essentially it will decide for a memory access whether it will lead to a cache hit or cache miss. All right, so this goes to the overview of our technique. I will also start with an example here. So suppose I have a program which take a secret as the input. So like I mentioned before, what we want to do is to figure out where is the secret dependent memory access. So essentially, we need to answer two questions here. The first question is where is the suspicious memory access is in the software system. The second one is how does it affect the cache behavior. So the intuition here is that to answer the first question, what we can do is to perform some program secret dependency analysis. So we essentially will find some memory access that have some dependency with the program secret. So to answer the second question, what we can do is to perform some symbolic execution and construct some symbolic formulas at the memory access operations. So essentially, symbolic formula represent the semantic of the program memory access and can be potentially used to further analyze the cache behavior to a certain degree. All right, so for this example, the program secret flow will be something like this. So we'll start from the secret and trace the dependency until we find two memory load operations. So this load operation depends on the program secret, and they actually represent the two table queries in the source code. And to use the symbolic execution, what we can find is two symbolic formulas that depend on the secret. So they represent the memory load operations in this example. All right, so after we got the symbolic formula of the memory load, the next step is to check regarding the cache line access variance. So our starting point is formula F, where the only free variable is the program secret key. So what we can do is to first substitute all the occurrence of the secret key in F with another variable k prime. So we will get another formula fk prime. Like I mentioned before, for a memory address of n bits, essentially the upper n minus l bits would be relevant to the cache behavior and to the timing. So what we can do is to redshift both formula for l bits. We also consider the conjunction of branch conditions because essentially it will give us a valid path to the memory access. So this is the constraint we constructed here. Essentially, this constraint proposes a question. The question is like, can different program secret? So please know that here k must not equal to k prime. So can different program secret actually lead to the access of different cache line? If the answer is yes, which means we will have some so-called satisfiable solution for this constraint. So it means that the cache line access here actually depends on the program secret. So in other words, by observing like access of different cache line, it is possible for the attacker to infer certain secret information from the running process. So this may be too abstractive, but anyway, we can go back to the example. So for the first table query, the corresponding memory access formula is like this. And the corresponding cache line access formula is like this. So here we set the L as 6, which is a pretty standard configuration. And to solve the satisfiability of this constraint, what we can get is a pair of solution, which k equals to 1 and k prime equals to 30. So how do we interpret the results? The interpretation is like a different key, for example, 1 or 30, can actually lead to the access of different cache line at this memory load operation. In other words, by observing the different cache line being accessed, attacker at this point may be able to infer some program secrets. All right, so for the next table query, the corresponding memory access formula is like this. And the cache line access formula is like this. So to solve the satisfiability of our constraint, we will get no satisfiable solution at this time, which means that cache line access at this point is actually independent of the program secret. So this means that at least on this execution trace, this memory access is free from the threats we are mostly interested in. Right, so this goes to the design of our research. So this is the design overview. So our starting point is the program and also the program secret. So the first step is to perform some online execution logging. So we essentially log a single trace at this step to facilitate the further analysis. So at this step, programmers can provide some inputs to cover some interesting code components. For example, he can intentionally cover some security-sensitive functions. So the next step is offline trace-based analysis. So we start with some tent analysis, where we treat all the program secrets as the tent seed. So this step will help us figure out what is the dependency of the program secrets. The next step is symbolic execution. So we leave the program secret as some key symbols and perform the symbolic execution on the tented instructions. So ideally, this will give us a number of memory access formula depending on the key and also some corresponding path conditions. So what we can do is to put each pair into a constraint solver. So if constraint solver would give us some satisfiable solution for these constraints, it will indicate that the memory access we are checking potentially leads to a vulnerable program points regarding our threat model. So this is about the tent analysis. So essentially, like I repeat, so tent analysis helps to capture the program secret dependency. And this is our tent propagation rules. So essentially, we have pretty standard tinting rules for the register. And for the CPU flags, we conservatively tint the CPU flag as long as the operands of some instructions is tinted. And for the memory, we deliver both explicit and implicit information flow tracking. So as for the implicit information flow, essentially it's like whenever the base register or some memory offset is tinted, we will propagate the information flow to the weighted memory content. So this is for the symbolic execution, where we utilize to construct the memory access formulas and also pass conditions. So we start by symbolize the program secret, no matter they are in the memory or registers, into some key symbols. And what we can do is to perform the symbolic execution along the trace on the tinted instructions. So here we also capture the so-called implicit information flow. So it's like whenever the memory addressing formula contains the symbol of key, we will create a new key symbol to represent the weighted memory content. So this one would preserve the implicit information flow. So we have a number of optimizations in this research to help us speed up the analysis and also provide some finer-grained information regarding the identified vulnerability. So here I will shed some lights on one of them, where we try to identify the so-called independent vulnerable program points. So like I mentioned before, we try to capture the implicit information flow by creating some new key symbols, as long as the memory address formula is a symbol, is a formula of key. So as shown in this example, for the load operation, we will create a new key symbol for the load output, since the memory address formula is a formula of key. So essentially, there are three situations here. The first one is there's no solution for the for this constraint. The fk does not equal to fk prime. So it means that the memory access is independent of the program secret. Please note that this is memory access, not the cache line access. So in other words, no matter what the program secret is, at this memory access point, it will always hit the same memory location. So naturally, what we can do is to, there's no need to create a new key symbol, since there's no secret dependency and secret information flow here. So the next step is that there's some solution for the cache line access model we are checking. So essentially, this part will be considered as a vulnerable point regarding our threat model, and we name this one as the independent vulnerable point. Some further vulnerable points will be considered as depend on this one. So the motivation is that by studying the underlying memory layout, so attacker could probably recover the relations, for example, some one-on-one mappings with the newly created new symbol and the input symbol in the formula. So as a result, the timing channel could probably leak the same piece or even a subset of information on the further dependent vulnerable points. We consider the independent point as the most likely attack surface, because essentially attacker need to spend some additional effort to analyze the underlying, to study the memory layout and recover some relations in case they want to attack the further dependent vulnerable point. But on the other hand, we assume the attack on the dependent point is still feasible, because essentially for the crypto system, where many pre-computed data structures are widely adopted to speed up the computation during runtime, it is still very likely for the attacker to analyze the memory layout of this load operation and recover some relations with the newly created key symbol and the formula fk. So the last situation is that there's some solution for the first constraint, but no solution for the second one. So it means that this memory load does not become vulnerable regarding our threat model, but still different secret can lead to the access of different memory locations. So we create some new key symbols to preserve the secret information flow. All right, so this goes to the evaluation of our research. So essentially, we evaluate 9 implementations of 3 commonly used crypto algorithms. So we write some sample code to trigger the decryption routines of each implementation, and we use the default configuration to build these test cases. So this is the evaluation overview of our research. So essentially, we identify some known vulnerabilities as well as some new program points that can potentially lead to the cache-based timing channel attack. So like I mentioned before, we put all the identified vulnerable points into the dependent site and the independent site. So here we also identify some known and unknown issues in the dependent vulnerable site. So like I mentioned before, this would indicate the most likely attack surface of your software system. All right, so for the scalability, so our tool process over 120 million lines of instructions within only 17 CPU hours. So we interpret the scalability as promising results. So we also try to explore the independent vulnerabilities and see how they can actually affect the cache behavior in a hardware simulator platform. So here we instrument the source code and modify secrets with the key and key prime, which provided by the constraint solver. So we monitor the execution of the instrumented code and intercept the traffic between the CPU and the L1 data cache. So we first report like memory access at all the vulnerable points actually leads to the visit of different cache line by instrumenting the code with different secret, the key and the key prime. And we also report like cache status in terms of hit or miss actually become different at most of the vulnerable points when instrument the code with different secret. So here we want to point out that we only conservatively check the cache status at the vulnerable point. So it is still likely like even at the vulnerable point, the cache status does not change. Different secret can actually lead to the different cache status at some further memory access. But anyway, here we only check the vulnerable points. So this is a case study of the RSA vulnerabilities identified by our tool. So it shows two RSA vulnerability in the libgcrypt. So all the program secrets and their dependencies are marked as red. And here we highlight two vulnerable points in the source code and also in the execution trace. So as I mentioned before, for each vulnerable point, the constraint solver would give us a pair of solutions like the key and key prime. So we also observe the cache behavior difference in the hardware simulator for both cases. So this example shows the hardware simulation results for the first case, where we instrument the program with the E and E prime I highlight here. So as you can observe, we can clearly observe the access of different cache line here. And also there's a big timing window of 3 hit versus miss by instrumenting the code with E and E prime. Also, this is unknown vulnerabilities identified by our work in the OpenSSL RSA. So essentially, this function tries to calculate the length of the secret key by bit. And to figure out the exact number of the last secret entry. So it uses a lookup table, and it actually leads to a secret dependent memory access. Yeah, it's an unknown one. And also we have found some unknown vulnerabilities in a C++ crypto system called Botan in the RSA decryption routines. So alright, so this is the summary of our work. We try to propose a technique that can identify the cache-based timing channel in the large-size software system. So our analysis is trace-based, and our model is simple but general enough to include most of the threads. So we perform some precise and scalable analysis and identify some known and unknown vulnerabilities in some real-world software system. Okay, so that's it. Thank you.
All right. Questions? What's wrong with you guys? Leaving it up to me. All right. I have a simple question, which is how do have you thought about generalizing some of this to things other than cache timing attacks? Like you have an information flow system and a symbolic execution engine, so like can you put this to work to do more than cache-based attacks? Like how easy is it to generalize to, like, I don't know, branch predictors and things like that?
I think we do not explicitly generalize it. It's just the way we propose a model to identify how the memory access project to the cache line access, and see whether the different secrets can lead to the access of different cache line. Yeah, essentially that's it.
I see. Okay.
So perhaps I missed this, but are you using virtual addresses or physical addresses for identifying these conflicts?
Well, mostly like trace-based analysis.
Okay.
Yeah.
Because
some like trace-based static analysis. Something.
Okay.
Yeah.
Maybe we could talk about this offline. So let's talk about this offline. Thank you.
Okay.
Hi, Cynthia Irvin, Naval Postgraduate School. Are you going to make this work available?
We do not have a concrete plan yet, but if you want to use our tool, please, feel free to contact with us.
Okay.
Yeah.
All right. Let's thank him again.